Cool. Hi, I'm Vishesh Panchal, and I'm going to talk about medical device automation. I just want to make sure that you can hear me okay. If you want me to speak up, give me a thumbs up, or speak down, thumbs down. All right. There you go. Okay, sounds good. So first, we'll just an overview. I'm going to talk about what the device is, what does it do, and then look at the overview as to what Scheme is, how we embedded Erlang in it to get the concurrency, and then how we implemented the fault tolerance and error handling, and then take a look at the DSL and the web servers, and then talk about the lessons learned, challenges, and the advantages of the approach. So what does a device, molecular diagnostic device do? Essentially, what we are trying to do is, from a sample, try and detect a certain strand of DNA or RNA. This is useful for detecting, say, HIV or CMV virus in a blood sample. What it does in chemistry point of view is, first it tries to purify the sample, get some DNA or RNA from it, and then add some food for it and basically bake it so that you amplify it and have billions of copies. You attach a dye to it and then detect it using a spectrograph. As you can imagine, trying to do this to process a bunch of samples, you need a lot of hardware. So we talked to 19 individual firmware boards. Each has multiple motors and sensors on it. And to give you a scale of how complicated it is, like you can see, like everything's moving at the same time. You can hear, I don't know if you can hear the volume. It's pretty hideous motor move volume, but you can, we can even make it play music. The motors move back and forth a little bit, and that plays music. And this is not just fake somebody playing music on a mobile phone. If you can notice, the belt's actually vibrating because the motor's moving back and forth. All right. So now to some more fun stuff. The overview, it's a client-server architecture. The client's a thin client written in C# and WPF. The server is where the magic is with functional programming. We wrote it in Scheme, and it has some of the Erlang embedding to get the advantages of the fault tolerance and message passing. The supervision architecture is actually borrowed a lot from the Erlang ideology. We have a DSL to enable chemists and scientists and other engineers to use the device. So the overview of Scheme is, like Dave said, the idea behind it is we have a small rules, and then we don't want to keep adding features to it. The idea is if you remove restrictions, you don't need a lot of features. For those of you who are not very familiar with Scheme, it was invented in '75 by Steele and Sussman. And it's one of the most important things for us is the first-class procedures and continuations, which we actually use to create the processes, implement processes Erlang style. It also has powerful hygienic syntactic abstractions, which is very useful to write the DSL. It makes it very easy to write it. We'll see a couple examples of it. And actually, one more important thing is the arbitrary precision arithmetic, which is useful for us in calculating the results. So Erlang embedding. First, let's look at records. It's useful because you can then, useful to use records in the sense that you can access data using field types instead of just index. And the example here is where declaration, we use angle brackets just as a naming convention, but here I'm declaring a input event record and then a few fields for it. And referencing is equally intuitive, where you just define what type of record it is, refer the actual object, and say what field you want to refer to. Copying similar to that is this would return you a object where the input state field would be set to a symbol called not running. The main reason we wanted this was so that we can do pattern matching really well. We don't have pattern matching in Scheme inbuilt, so we implemented pattern matching like that's in Erlang. And it can pattern match strings, symbols, vectors, records. And it also allows you to do other things like when you have some matching, when you're trying to match something, you can not only match on a symbol or a string, but you can also match on an instance of a variable. Like I have here where rack count is being matched to a variable called starting rack count, which is scoped locally. You can also, within that match, bind values to a field, like is processing input is being bound to a local variable called is processing input, which you can just use in scope. And it makes for very succinct code, which is also very readable. And then the comma underscore at the bottom near the void, that's basically a match with any pattern. So this gives a lot of strength for us in terms of pattern matching, but also makes for very nice and readable code, which I think is important. Then to implement the OTP layer from Erlang, first to implement the processes, we used one-shot continuations and software timer interrupts, which made for a very lightweight process implementation. And then we implemented the gen server patterns, and it's a nice functional way of serializing messages and mutating the state. We have basically implemented the Erlang model, and if you're familiar with it, the init, handle call, handle cast, handle info, and terminate. We didn't actually implement the code change part of it just because we never felt the need for it. I don't think the FDA would appreciate us just changing code on the fly, so that was there. The event manager is basically a subscription service to a centralized sort of service which will let you subscribe to certain events and acts as a intermediary. The supervisor are the main mechanisms which enable doing some of the error handling and fault tolerance. They basically monitor processes and other gen servers, and their main task is to either restart and, or if you cannot restart a service or a part of the system, then at least handle shutdown gracefully and have enough logging so that you can actually look at the problem and figure out what went wrong. So how do we actually use these models? Firstly, the system's decomposed into a lot of processes. Each process tries to do what it's supposed to do. There's no defense in programming, and then we let it crash. And this is all borrowed from the Erlang mantras of error handling. And processes can monitor other processes, and then the fault tolerance is gained from the supervision hierarchy. One of the most important things was, since we are talking to hardware, hardware is going to fail. Sensors might fail, motors might stop moving, bad things can happen, and you don't want it to be a, oh my God, something bad happened, you can't react to it, you just built this in. This is supposed to be designed in, you want to be able to handle stuff like this. How do you actually execute something on that system? So we have a DSL where somebody is going to write what they want the instrument to do. A specific instance of what they want to do is called a recipe or an assay. And then we take and read in that assay and run it in a confirm mode. And we are trying to help out the people who are writing these assays by telling them if they are missing any resources or trying to use the same motors in 2 different instances or something like that. Give them hints about how to allot time and how much time to allot for each action. And then you just queue that instance in and you schedule it. And the scheduling is actually not that hard in this case because we don't move previously scheduled devices. It's essentially like playing Tetris. You just have existing resources being used and you find the best slot and you slide it in there. Each action, which is basically a set of steps, like motor moves or pipetting liquid and stuff like that, is run in its own process. This is so that if things go bad or something bad happens, you actually have options now to either ignore failure or say cancel that one particular set of actions or just stop the whole device because it's something catastrophic. But it gives you programmatically options in doing things rather than just have the whole system shut down. So why we focus on error handling and fault tolerance so much. And this is an example from an article called Sound Verification Techniques. And this is about a radiation therapy device where they had a couple of issues which basically had the patients receive radiation up to 30 times higher than recommended amount. And as you can imagine, that's really bad. And the couple of errors they had one was because they were using shared mutable data, and that's why we use message passing concurrency. The other issue was an overflow of an 8-bit integer. And this is where the arbitrary precision mathematics comes in handy because we use Scheme. Another example is REN5. This was a rocket launcher where the whole launch pad was destroyed and so was the payload. And the reason was that there was an overflow when they tried to convert from a 64-bit float into a 16-bit integer. And we wouldn't have this sort of a problem in Scheme because in Scheme, the conversions are preserve information, and if it cannot, then it raises an exception. With our current architecture, it would have basically been caught at some process, and either the process would have died and we would have safely shut down, but at least we wouldn't have a silent corruption or failure, which would later cause destruction. And even the smart people who design space shuttle simulators and stuff, they had a similar issue where after they were doing an abort procedure, the whole computers crashed because some of the counters weren't being reinitialized correctly, and the code started jumping into random points in memory, which, as you can imagine, is pretty catastrophic. One good thing is Scheme code cannot jump to random points in memory. And counter management is slightly more hard. I mean, certainly you can make a mistake even when you write a gen server. But the good thing is then the gen server will crash, and the supervision hierarchy then comes into practice, where at least it will stop the whole system and not create crashes and not know what to do. So next, let's talk a little bit about the DSL. So the DSL was written mainly so that we could have the scientists and other engineers, hardware engineers, electrical engineers, be able to use this instrument without having to be handheld by software engineers. We didn't want a layer of software engineers that they need to talk to so that we act as the gateway of this is the only thing you can do on this instrument. So we wanted to give them a DSL which enables them to basically use the instrument the way they want to. So from a scientist point of view, they want to think about steps like what reagents to add, what do you want to do to the instrument, what mixing do you want, and how much to bake the sample, what kind of temperature experience you want to give to the sample. From engineers' point of view, they want to look at reliability, so run motors over weeks and move stuff around, look at timing, look at variability. So we tried to provide all of this in a DSL, which made for a very complex DSL. And we sort of roughly divided into between the extraction purification of DNA. So that part of the DSL exposes how to load a tip or construct at that level where you're talking about pipetting, moving magnets, incubating, and thermocycling, taking spectrographs. But then for a lot of engineers, they can do stuff like that's on the right side where they can define what aspiration protocol is and what dispensing protocol is, or how to move motors, and even low-level stuff like controlling valves. So let's look at an example of a DSL construct. So on the right is the English version of what a scientist probably wants to do. So they want to bake the enzyme for a minute at some temperature, 37, do a couple more bakes, one for, say, 95 Celsius, and then they want to cycle 40 times and bake for 5 seconds, 20 seconds, and then wait for some time and take spectrographs. So the DSL for it looks very similar to English, where you say bake what you want to do and for what time and what temperature. It is also very forgiving. It allows you to define time in multiple units. You can do 1 minute, 60 seconds, or something else over there. The parts which define enzyme, RT, enzyme activate, that's basically essentially syntactic sugar for the scientists, because software is not going to use that part, but it makes it way more readable for a scientist, and they know what they are doing or writing this down when they're writing this part. The cycle 40 times is equivalent there, and then the bake construct actually takes an optional clause to read the spectrum, where it's saying is it'll wait for 10 seconds and then basically take 2 pictures using a red and a green laser. And then I want to show exactly how easy it is to write macros in Scheme. Here we're just looking at a simple one. It's the cycle abstraction macro, and you can see it's just basically a do loop. That's all it's doing. It's matching. It takes in auxiliary keywords like time and times. So one, we make the DSL squishy so that somebody like a scientist is trying to write this. We don't expect them to be software engineers. We don't expect them to be able to write do loops where if they got the initialization wrong or the condition wrong, they are either off by 1, or worst case, they are going to loop infinitely. So providing an easy way for them to do something like a cycle makes sure that, yeah, they don't have the power of a do loop and be able to do a lot of things that would, but they don't need it, and make it easier for them to write error-free stuff. And then also allow them like time versus times. It's not strict to have the keyword as plural or singular. Allow them to do it. It's fine. We know what they are trying to do. And that's an example of the usage, and it's just clear as to what they're trying to do right there. Lastly, a lot of this boils down to, because we have these devices, and this is in the development phase especially, there's a lot of debugging going on at a system level, figuring out what goes wrong, what's happening. So we implemented a web server and a S-expression-based sort of DSL just for programmers to write it, so that we can not only emit HTML code, but use the power of Scheme in it. And this way we can actually debug instruments remotely. So the instruments, in a different part of the country, and we can just log into our network, go access that instrument, and we can even visualize the data. It also gives us the ability to provide some of the UI functionality from a web-based client. That way, we can actually do fast prototyping of UI without having to go through the whole client and making it up and then iterating over it. So we can get some fast iterations on the web and then move it to the actual client, C# client. The engineers also like it because we provide JSON. We implemented JSON, and this is used by engineers to grab data from instruments remotely, which can be fed into other tools like validation tools, which is important because we have to send all this testing data to the FDA because we are in a regulated space. So some of the lessons learned, message passing is great. It makes it easier for us to talk about concurrency, but it's not a silver bullet. You can still shoot yourself in the foot. You can get deadlocks between gen servers. In fact, we had a couple of cases like that where you could run for a week and nothing would happen, nothing would go wrong, but then suddenly something deadlocked and caused an error. The good thing is you have timeouts in your gen servers, and logging at higher supervisors, so that if at all it went wrong and something bad happened, even if it happens at a low frequency, it'll be caught correctly, you would have logged data, and you can debug it. The supervision structure was hard to build up, especially because as far as we know, we were breaking ground on this kind of stuff. There wasn't much to just go on the web and look at and say, oh, give us an example architecture for automating devices. And then the DSL gives a lot of power to folks who are non-software engineers, which also means that when things go wrong, you have to spend a bit of time in support because they're not as efficient in Scheme, and you don't expect them to be. So you have to be prepared to provide support and be able to help them. Like I think other people mentioned, hiring is hard, and you don't blame candidates who are getting hired into essentially a unique environment of Scheme and Erlang, and they're trying to learn, basically a new way to write programming, like functional programming, and not only that, but also learning this hybrid new language, and then it doesn't make it easier for them because there's no IDE. We use Emacs, so there's no autocomplete as such for them. Or when they compile their programs, if they find an error, they can't just go to Stack Exchange and type, copy paste the error in and say, hey, what's going on? Like, can somebody help me? They have to come to, the people on the team. And I think, like many other presenters said, you have to be evangelical about it, and you have to help out, and that's the only way to get everyone up to speed. There's some unique challenges which come with dealing with FDA, and not just the FDA. I imagine this is true with any regulated space where you're looking at metrics like defect density. Scheme is very terse, so I mean, just to give you a sense, all of our instrument server code it's 50K lock. And our thin stateless client, which is not actually doing any logic-based processing, is almost double that size. So, defect density and these metrics get very skewed because of this. And then FDA is pretty, it's scared about new technology like this, where they don't know, they haven't seen this before. You're using all of these open source stuff. We don't know where it came from. How do you know this is good? How do you know this is bad? And rightly so, because they don't, and we can't give them a good explanation. So the onus is on us to say, hey, this is good stuff, and and one way to do is actually do good documentation when we are writing this software. So that's that kind of is important to do. And then the good part. So the great part is message passing concurrency actually allows you to think parallelly, make the reasoning easier. So when you look at code, you can actually inspect and review code. It's easier to understand what's going on, and you can argue and design the code well. Fault isolation is, and the supervision tree gives us the ability to debug stuff very nicely. And even when we have problems where things are running well for a long time and something goes bad once in a while, you know that you're going to get enough logging and tracing to figure out what went wrong. The let it crash philosophy is great because we write code which is quite compact and terse. This not only reduces the time in coding, but also in testing because they have fewer test points to check at. And then strong typing and runtime checks provide failure and exceptions rather than silent corruption, which is important because, as we saw a couple examples, silent corruption then eventually leads to catastrophic results. And lastly, mixing of languages is really useful. We really like the syntactic abstraction of Scheme, the arbitrary precision, but then we also wanted to use the message passing of Erlang and the OTP framework. So we said, make the best of both worlds, and it makes it really, really useful and nice to be able to use the good parts of all languages rather than having to choose between one or the other. And DSLs not only make it easier for the non-software engineers to use the device, but it also helps in rapid prototyping just for software engineers as well. And that's about it. The references, Joe Armstrong, and then the first one is the article from which we took the examples of the failures. And here's my contact info. Any questions? Few of them.
Let's say that in your earlier example of DSL, someone would, instead of cycle 40 times, cycle FOR and UI. So then they execute their full DSL program. What happens machine-wise?
We would give them a compile time error, basically, essentially. So yeah, FORTY would come back as a symbol, and it would, when they try to enqueue that particular assay, they would get an error saying yeah, invalid symbol 40 or something like that, or expect a number. So yeah, they wouldn't be able to run it. The confirm mode itself would basically spit out, hey, this is wrong. So they won't get through like 3/4 of the assay and then get an error saying, oh, by the way, we can't do this. So. Yeah.
You mentioned strong typing is good.
Mm-hmm.
I'm not going to argue with that, but you said that you were using Scheme, which is dynamically typed. I was a bit confused.
Right, so it's dynamically typed, but it's strongly typed. If you try and convert things from one to the other, it expects the type to be correct. Certain functions take in, say, integer. So it expects to be passed in an integer. It won't actually type check it when you compile it, but then, yeah, it needs that. It needs an integer if you write a function which is going to act on an integer, especially. So, yeah, I mean,
Which style of Scheme were you using?
we are using Chez Scheme. Yeah.
Good graphic. Obviously, we record static as well as dynamic typing.
Okay.